I'll be finding. And which test is this? Chapter 2 test. Okay. So I can see the same one you're talking about. There's test 1, test 1, test 2. Got it. Okay. And which number? 6? Okay. All right. I thought that was probably it. Okay. Okay. No, given that 2A inverse, that's 2A inverse right there. Okay. Right. So what I would suggest to you, what would be your steps, you think? What original A was? What is A? Right. Right. Okay. That is certainly one way to do it. Certainly that seems legitimate. Another way, and you can try it both ways and see what you like better, you can just take the inverse of this one, and that's a 2 by 2. That's going to be pretty easy to do, right? And that will give you 2A, and then divide that by 2. So yeah, either way would work. Uh, well, yeah, if you take the inverse of that one that's right there, the inverse of that uh, right there, then you'll get 2A, right? Okay, and then you can divide 2A by 2 and you get A. Does that make sense? All right. But I think the way you said of doing it, I think would be perfectly legitimate as well. Yeah. That, yeah. All righty. Good deal. Okay, good. All right. It was a different looking problem than what most of them are. Uh, right, right. Good deal. All right. Well, since we're already at it, any other questions? Issues, concerns, anything? Let me say one that I have, and it is that I look at my grade book, and this is, of course, the best class I've ever had, just top of the line. However, I only have one research paper has been turned in by this, my best class ever. Okay, that doesn't seem to be congruent. Something seems to be wrong with that picture. So, folks, what I'm trying to say is please I'm saying this to everybody because I hope they'll go back and listen. Please get your research papers in, because guess what? This is your last weekend coming up to work on it, if you were planning to work on it in a weekend, because next week is the last week of class. Okay? Which means that Tuesday will be, that's when I really would love to have the research papers in. You can turn them in Thursday this week if you want to. I'll be happy to take them then, or anytime, because you're going to send them to me email or Blackboard message anyway. Anytime you can get them to me would be great, but I'd really like them in by next Tuesday, because next Thursday is technically final exam day. Okay? Which means that at the end of class on Thursday, I will be giving you your final exam. I'll be putting it out there on Blackboard under messages. So please try to get the research paper in by Tuesday. Earlier if you can, but Tuesday's the last day before you start losing points for it. So please, I don't want you to lose any points. Now, he's not here now, but there's one person who still hasn't turned in test 1. I need that. And as you were just asking about test 2, I don't have any test 2s yet, so I'm glad you're working on that one. And test 3, I gave you probably last week sometime, or maybe the week before. I don't have any of those yet. And we're coming right up on the end of the term, so basically this is also the last weekend really to get that first and second and third test done, okay? And get those into me sooner rather than later, but please try to get them in because I'll be giving you the final exam next Thursday, sometime after class, and you don't want 2 or 3 tests hanging on you, or even, as one person has right now, a research paper and 4 tests. Okay, no, that's not right. That's not good to do to yourself or anybody else. So please, this is not just for you, James, because I know you're going pretty much on top of things, but everybody else, please get your research paper, your first, second, and third test in, so next week you can just focus on the final. Okay. Yes. Yeah. After you find 2A, which is the inverse of that 2 by 2 that you have there, then you divide 2A every term in 2A by 2, and you get what A is. Right? Of course. Oh wait. Oh, as you did what? Okay. In other words, you did 1/2. If okay, if what you were telling me, well, I understood you to say that was one way to do the problem, and then when you do it the other way, it should give you the same answer. If that's what you're saying. Um, well, you find the yeah 1 over the term. Yeah. Okay. Okay. Right. Yeah. Yeah. By that matrix by 2. Yeah. Every term in there by 2. Right. As what? Yeah. Yeah. It sounds like you do. Yeah. Yeah. If you did those steps, that should be right. Uh huh. Okay. Excellent. Okay. All right. Glad you did. Okay. Any others before we get going on chapter 4? Okay. Well, I know you're good, but do you have any more questions? Oh, no, I'm just kidding. Okay. All right. Okay. All right. Let me get my pad in place. Sorry, I've got frog in my throat. And get my stylus in place. And what we're going to do is vector operations in R4. Okay, this is example 5. We're on page 156 if you have a book. Chapter 4, vector spaces, and 4.1 is vectors in Rn. Now, what we mean by that is we're looking at vectors in spaces that are defined by an n dimensions of your real number axis, basically. Now, I can't visualize any more than 3, but technically they can be any finite number n of spaces, whole number n. Okay, so I'd say counting number n or natural number n. Okay, so let's do R4, a vector operation R4. This is example 5 on page 156 if you got your book. All right, here's what you have. You have vector u, which is 2, -1, 5, 0. 2, -1, 5, 0. That's certainly a vector in Rn. 4 components to be in R4. I'm sorry. vector v. Now in other texts he puts these in angle brackets. I want to do that, but he does parentheses here, so we'll do parentheses. This is 4, 3, 1, negative 1. 4, 3, 1, and negative 1. Yeah, get out of there. And usually when it does something like that, it erases something sort of randomly. Okay, here is W. And that's negative 6, 2, 0, 3. Okay, 3 vectors in R4. It says find x using each equation. So here's what we're looking for, vector x. And the first one here, the A one, says it's 2u minus v plus 3w. Okay, so I'm going to start by doubling u. What would that give you? Okay, yeah. Good start. Okay, minus. Now I'm going to try to do these two operations at once, but if you want to string them out, we can. What you think? Okay. Okay. So that would be, if I can get my cursor to move, 4 plus 3 times the negative 6, right? That's 4 minus 18 would be minus 14. Okay. 3 plus 6 is 9. 1 plus 0 is 1. Good answer. Okay. Negative 1 plus 9 would be 8. Okay. Yuck. This one I have to hit my knuckle on something. Okay. Did you see anything happen when I did that? You just heard me say yuck. Okay, yeah. You see it, you don't see it, I see it, and it freezes my screen and everything until I clear it. All right, I think we can do this pretty well, can't we? 4 minus a minus 14. Okay, they're there to trip you up. That's the only purpose of a minus sign, to trip you. Okay, it did it. Okay, what would that give you? 18, comma, negative 11, perfect, comma, got it, comma, perfect. Let's see how the book did. They got 18, negative 11, 9, negative 8. I'm so proud of them. That's just amazing. Okay, let's try to work the B part down here right underneath that. That's 3 times vector x. Ooh, they're making it tougher for us now, plus w. Is equal to 2u, as in happy birthday, minus v plus x. Now, I don't know if you remember working things like in physics or other places like that, where They talk about whether you solve the equation by plugging in and solving, or solving the literal equation first and then plug in and figure out your answer. I call it plug and chug or chug and plug. In general, it's easier to deal with the literal equation first. So in other words, let's do the general operations here before we ever plug in the values from up there. What do you get then? Perfect. Yeah, I got you. Equal to. Okay. Now what would you do? Okay, I agree. Let's subtract an x, vector x from both sides, and also let's go on and move our 3w to the other side. Okay, so that gives us, as you were saying, 2x is equal to 2u, as in happy birthday, minus v minus, these add to 0, minus 3w, right? Alright, now let's plug and chug. Let's do our plugging. Okay, we've already chugged. So that'd be 2 times u. Yes. Yes, you could. You certainly could. And then you'd have u minus half of v plus minus 3 halves of w. Okay, you must like ugly, huh? Okay. No, I tend to put off the fractions until the last possible moment if I can. So you can certainly do it the other way. It's a perfectly legitimate move. But let's see what we got. The numbers will be a little bigger, but at least they won't be fractions until the very end. So let's see what we get. Okay, so 2u would be, I can't find my cursor. Where is it? Oh, there you are. Oh, wait. Here comes Aaliyah. Let me get her in the course. Okay. All right, the bottom part of the alphabet is here strong, the top part missing completely. Of course, when I say top part, that's a D and a P. This is heavy on the bottom part, but welcome, Aaliyah. Okay. Aaliyah, we're on in Chapter 4, Vector Spaces, 4.1, which is vectors in Rn, and we're doing a problem, example 5, on page 156, which is dealing with vector operations in R4. So that's where we are. We're on the B part of this. We've already done the A part. It's on the top part of the screen. The B part is where we are now. So let's proceed. What we were doing, we got 2x times vector x. We're looking for x. There it is. Okay. We're not going to mess with the 2 yet. James wanted to, but he just works too hard for me. And I'm going to now just do the right hand side. Double u. Well, the u is up here. So you tell me what vector that is. Doubling u. Now I've got to get my, yeah, okay. What you get? Yeah, there it is right there, isn't it? 4, -2, 10, and 0. Okay, we doubled the u part. Now we're going to subtract v. So v is 4, 3, 1, -1. That was just writing it down. Minus 3w. So you tell me what to put for the 3w. Or did you want to go on and do the minus times it? We can make it a plus if you want to. In fact, I could have done that. Okay, so that would be negative 18. Hold a moment. Here's Ricky. Okay, so Ricky's here. 3 out of 4, and one more come in, and we got a full house. Okay, so I'll let Ricky get connected before we get going. Okay, Ricky, good to have you. We're in Chapter 4, Vector Spaces. We're in 4.1, Vectors in R to the nth, Rn. And we're doing example 5 on page 156, and we're on the B part of that. At the top of the page here, you'll see what the three vectors U, V, and W, they're all R4 vectors because they have 4 components, okay? And we're doing manipulations with them, and the B part, let me go on and write this in since James and I were here alone. I didn't keep housekeeping too well. There's the A part up there, we got an answer, and here's the B part down here that we're working on that answer. We've already got it so far as 2x, we're looking for x, but we got 2x is equal to 2u, which we've got written there, minus v, which we've got written there, minus, and then we're doing 3 times w, so that's the 3w from here. We're tripling this w here. So we got the first term minus 18. What's the second term? 6. Third term? Fourth term? 9. Okay. Now, next to the last step here is figuring out what this is. So here's a 4, and there's a minus 4. So that adds to 0, and you wind up with a plus 18. So that's going to be an 18 there. Second term, a minus 2 here, minus a 3 there, that gets us up to a minus 5, and then a minus 6 on that would be, I think, a minus 11. Okay, then we have a 10 here, minus a 1 there, that gets us down to 9, and then subtract 0, and I think we're still at 9. Then we have a 0 here, minus a minus 1, that gets us a plus 1, minus 9 would give us a minus 8, right? All right, and that's what 2x is, so let me go and write that down, 2x. We want to know what x is, so what do? Divide every component in there by 2. So that would give us got it? Hey, yeah. Divide by whatever number you want to. It's a free country, okay? -4, okay. Who am I to constrain you to the truth, huh? All right, let's see what they got as an answer. 9, -11 halves, 9 halves, -4, yes. Okay, that is example 5B. Now, I know some of you came in a little later after we're going on it. Are there any questions of the parts that we did before you got in the room? Everybody got it? All right. Let me pause for just a moment here. And I know, Aaliyah, you said the one you asked me about on the, let me back off one. If y'all listen to the first part of this YouTube video when it gets out there, and that's probably going to be late this afternoon, possibly into the evening. I don't know when I'll get that on the playlist. It'll upload most of the afternoon, and then for the if I can get it done before my 5 o'clock class, I'll put it out there on the playlist, but otherwise it'll be after the 5 o'clock class. That ends at 6:30, so it may be as late as 7 or later before it gets there. But if you go and listen to that, James had a question about problem 6 on test 2. and we didn't actually write anything down. I was getting, well, I think I wrote something down, but we were talking about that. So if you go back and listen to that, you'll hear me talk about it, and hopefully you'll follow what we were talking about. I didn't write down the answer or anything else. I don't do that, but there. Now, Aaliyah had a question about another problem on test 3, and I gather from your response my answer to you was okay on that. Okay, good. All right. Are there any other questions before we go any further? Um, and one reason I'm asking that, I want to stop and say this. I forgot to say it to my first class, and I regret that. Ricky, you were in that first class, but you're in pretty good shape there. Um, but what I was saying, and I meant to say in the first class too, this class I've only received one research paper. Okay, they're due next week. So that means this coming weekend is your last weekend to work on it. Now, if you can get it done before then, turn it in before then. You don't have to wait till the weekend to turn it in, but please get it done. Tuesday is our last day of class technically, and technically final exam will be on Thursday. But what we're going to do, because we're sort of far behind, we'll go on and have class on Thursday also. I'll answer any questions you have about anything, and then wrap up and get to the point where at the end of class I'll then give you your final exam. I'll put it out there on Blackboard message. I'll put it out there, and then you will have, Thursday, Friday, Saturday, Sunday to turn it in. Please try to get it in to me by the end of the day on Sunday, because I think they want us to have grades in by not this coming Monday, but the next Monday morning, Monday at noon. So please try to get all your work into me. I want everything else in next week, as in the research paper. I'd love it in by Tuesday, because that's technically the last day of class, even though we'll still have some things doing on Thursday. But technically, Tuesday is the last day of class, so that's when the research paper is due by Tuesday. Okay? Your first, second, and third test, now I'm preaching through the choir on this because all three of you have turned in the first test, but one has not, so I'm saying this for his benefit. That also I'd love to have in soonest you can possibly do it, definitely by Tuesday if you can. Second test, which I've received 0 in so far, I'd like all those in if you can possibly do it by Tuesday. And the third test, which I know you're working on because you've been asking me questions, I would love that to be in by Tuesday. Sooner if you can do it. If you can get any of these. Okay, yeah, that's right. I'm sorry. I don't have it graded yet, but you're right. You did turn in the second test. I forgot that. I I think it was this past weekend, wasn't it, that you sent it to me? Okay. This is what I got this past weekend. Okay. And yesterday I thought I would make a dent in grading these. I started the morning printing more tests that came in. Not all these came in over the weekend. Some came in yesterday morning. Printing more tests. Then I ran into an email from the dean that she wanted me to call, and I knew that was going to be bad because she loves to talk. And so I was on the phone for way too long with her yesterday morning, and finally she had something else she had to go to, thank goodness, so we got off of that one. I went back to printing tests, and then the associate dean called. And then by the time, just about the time I got all the tests printed, it was time for me to teach my first class. So I got 0 grading done yesterday because of this. Okay, so today I had hoped to get grading done this afternoon, but I'm advising for 2 hours this afternoon, and 3 of the 4 half-hour slots are already taken. So there goes an hour and a half of grading I won't get done. So I do have a little bit of time before the first appointment, so I'll try to get some grading done then, and then the last appointment goes right until my class time this evening. So I'm hoping to, once the evening gets here, I'll take these papers down and try to get grading done then. Last night I was going to do some grading, and they sent me an email that I had to respond to last night, so that ate up the rest of my evening. I had to do some background research and do other reading and stuff like this, so I got 0 papers graded then. Hopefully that won't happen tonight as well. Okay, but please, I'm going to try my best to get as much grading done as I can this week and get the grades on Blackboard sometime. Now, we're out of town this weekend, and I cannot promise I'll have any time to do anything while we're there. We've got to go over to the farm and take care of some things with trees, but if we get any rain, which right now I'm hoping for, then I'll be able to go inside and get some grading done. But I will not be able to post any grades from there. I don't think I will, because the internet over there is so incredibly slow and sporadic. I'm not sure I'll be able to even get on the internet. So if you turn in something this weekend, I may not see it until, may even be Tuesday afternoon, because we drive back Monday morning and I come back and have time just basically get ready for my first class. I'm in class until 6:15 that evening, and then I have class from 8:30 to 1:15 Tuesday, so it may be Tuesday afternoon before I even get to grade anything or even print anything you turn in this weekend. So try to get it to me sooner rather than later, but get it to me by Tuesday so I can add to I can get as much of this graded as I can between now and then do the grading on that next week. So it's down to the short rows now. I mean, I'm in a pinch. I know y'all are in a pinch. Please get as much done as you can, as soon as you can. And when you finish one thing, go on and get it to me. Okay, then work on the next one. Then get it to me. Don't wait and send them all at once. I mean, you can, but I'd rather have them as I can get them. Okay. All right, that was the page political announcement. Any questions? All right, I'm hoping Jermanuel will be listening to this, so he'll know to all that information as well. All right, that gets us to the top of page 157. All right, top of 157 is talking about, starts off with their favorite zero vector again. Okay, now the zero vector in Rn, just like it is in R1 and R2 and R1, it's the number 0. Okay, in R2 it's the ordered pair 0 0. In R3 it's the ordered triplet 0 0 0. Okay, you get the thing here. The thing about it, it has no magnitude and it has no direction. Okay, so it's not a very good vector, but you have to have the zero vector there. Well, the zero vector in Rn has n components. This one was R4. It had 4 components. So Rn is going to have n components. And every one of those n components has got to be a 0. Okay? That's the zero vector in Rn. It's also the additive identity element in Rn. Okay? Because anything you add in Rn to the zero vector in Rn, it's going to get you the same thing you started with, because you're not adding a thing to it. You're adding zeros to every one of those elements. So it's the additive identity element. Similarly, the vector minus v, say this was a vector v in R4, minus v would have been -4, -3, -1, 1. That vector is the additive inverse. Because if you add that to v, v plus minus v, you're going to get the zero vector. Okay, so that's called the additive inverse. The additive identity element is the zero vector. The additive inverse of any vector in Rn is going to be exactly the opposite of that vector. Every term is negated. Every component is negated. And when you add the two together, you're going to get the zero vector. So the next theorem summarizes several important properties of additive identity and additive inverse in Rn. And hopefully these will make perfect sense to you, but in case they don't, they're true. Okay? Now, typically I don't like always writing all these things down, but since, do all of you have books? I know you do at one time. Do you have them in front of you? Yes, all three? I heard two yeses. All the microphones are muted. The one that didn't mute didn't answer. Well, let me go on. It's not going to take too much to do them, but just so I'll have a talking point. So, where we start is the given, and the given is V is a vector in Rn. And here's how I express that. It's an element of Rn. It's written as a superscript n, but nothing is raised to any power. That's just how we write that space. C is a scalar. Any scalar, any real number, positive, negative, fraction, decimal, rational, irrational, any real number, including, it could be zero, but usually we don't use zero, but it could be any real number. Okay? Then the following properties are true. Okay? The additive inverse is unique. I'm going to abbreviate like crazy. Additive inverse. Now this is nothing to do with a matrix inverse. That's not what we're talking about. That's the thing of minus the vector. So if V is a vector, its additive inverse is minus V. That additive identity is unique. I'm sorry, I said it wrong. This is the additive identity. So let me erase that. I was jumping down to the next one. Sorry. Okay. Okay. And this is really a dumb one. That's why I was almost mentally skipping it. The additive identity, which is the zero vector in Rn, that's open parentheses, 0, 0, 0, 0, 0, 0, n zeros, close parentheses. Okay? It's unique. In other words, there's only one of them in Rn. There's a separate additive identity for every separate space, but for Rn, there's only one. Okay? And how that is expressed, and this is a little bizarre, but it is how it's expressed. If V, no, this is right, V plus U is equal to V, then there's no way around it. Yuck! Get out of there. You can't see it. Okay, I'm trying to let that fade away so I can write. You probably couldn't see any of that. What this implies is that U then, this U right here, would have to be, no way around it, the zero vector in Rn. Okay? Has to be. There's one and only one that'll make it work, and it's always the zero vector. Okay, number two. The additive inverse. This is what I was writing before. Is also unique. Okay? I should say additive inverse of V. Okay, V was the given vector. Okay? And what that means is that if you have V plus U, again, They haven't even mentioned what u is, but u has to be a vector in Rn, and that's equal to the 0 vector. Then that implies, without a shadow of a doubt, that u has to be the opposite of v. No way around it. It's one and only one vector that'll do that, and that would be the additive inverse. Okay, so u would have to be the additive inverse. Now, number 3. This is one of those duh ones. Well, I don't know why it did that. Number 3. The scalar 0 multiplied by that vector v in Rn, guess what it's going to be equal to? Has to be a vector in Rn, and that's the 0 vector. Big surprise there. You multiply 0 by every element in v, and every one of them turns out to be 0 once you do that multiplication. Okay? Number 4 is almost as blatantly obvious, and that is c, any old scalar c, not necessarily 0, any scalar, 4,565,084 times the 0 vector. Guess what that's going to give you? The 0 vector. It's going to be a vector. Okay, multiply a scalar by a vector, you get a vector. Okay, now number 5 almost is a compilation of the previous 2. What if you knew that c times v is equal to the 0 vector? Now, there's either one or two things have got to be true. What would that be? Right? Or, but don't just say 0 is the 0 vector. Those are two different things. 0 is a number, c, scalar, and v is a 0 vector is a vector, same dimension of v. So one of those two has to be true. And that's pretty obvious too, I hope. And then let's do number 6. If you do the opposite of the inverse of v, guess what you get? You get v again. Just like you do with real numbers, everything else, the opposite of a negative is a positive. Okay? So whatever v was, the inverse of v is the opposite of that. Every component of v got changed to sign. Then when you do the opposite of that, they all get changed again back to the original v. Okay. Now, I think we've talked through just about every one of these, so I'll let you read through the proofs and see what you get. At the bottom of page 157, there is, I believe James has had physics. Of the other two of you had physics yet? I think Aaliyah said no, right? Ricky, have you had physics yet? I think maybe so, but I can't remember. Okay, good. I thought so. Okay. You've run into this problem, I know, in your mechanics class. You got the boat, the truck pulling the boat out of the water, and you write that as a vector problem, and then you solve for what force is needed to pull or whatever. That can be done with linear algebra also. Now, you're using vectors, so of course that is using a vector space, though you probably didn't think about it at the time, but it is. Excuse me. Now, I guess what they want you to do, because they do say verify something, I guess I ought to, because some of you haven't had this before. Okay, what you have here is a ramp. And let me see if I can figure a way to do this reasonably. Okay, let me first get by getting straight lines that'll make it look a little better anyway. I'm going to try to draw a horizontal line here. That's fairly close, but not really all that close, okay? And I'm going to try to draw a vertical line here. Okay, that's not quite vertical, but let's just imagine that's true. Okay, and I'm also going to draw another line connecting the ends of those. So I'll start here. Well, this drives me nuts. Start here. It's not doing it. Okay, if I hold the pen down too long, okay, that's kind of a ramp. They're supposed to meet at the corners. Two of them didn't, but one of them did. Okay, now let's go back and get my pen back. And this is what they call the, well, none of the three met, did they? This is your angle theta. That's the angle of the ramp. Okay, now the boat is here on the ramp, and we're going to pretend it's a single point right there. That's the boat. Of course, the boat's much bigger than that, but one of the things in physics we do a point, although they have a name for it, I can't remember what it's called now, but we just let a point represent a mass. Big old mass, but let's say it's all concentrated at that point. Because it's a mass, then I think I will go back to my drawing here. The weight is always pulled to the center of the earth. So the weight is always vertically downward. Now that's supposed to be vertical. It's not quite, but let's do. All right. Now, there is also what we call a normal force acting on this. That's the ramp pushing up on the boat. Okay? And why is it doing that? It's not supposed to be vertical. It's supposed to be any old thing here. Okay, that's supposed to be perpendicular there. This is what we call the normal force. Whoops. Get back to my text. Okay. Okay. Now, that is the by Newton's third law, the force, the ramp is pushing back on the boat. Now I don't have that anywhere close to perpendicular, but if I were to, and this is not going to be pretty, I'm sure, to do the opposite of that normal force down here, and why is that not drawing? Because it won't draw. I don't know. Okay. Okay, there's the opposite of the normal force there. So that's minus the normal force. That's the boat pushing down on the ramp. Okay. Now if we connect the dots down here, this will be the weight. This is the force, and I'm going to go back to this mode. Okay, the weight is a force, so I'm going to put a vector on that. The normal force is a vector, and it's not going to draw. Irritates me. Okay, and of course its opposite would be a vector too, but this would then be the force that the truck is having to pull the boat up the ramp. Okay, now here's kind of the physics of that, and this is put strictly in layman's term. Part of the weight of this is the weight, by the way, that's a vector, and this is the force that the truck has to pull to get it to go up the ramp. Okay, now this component here, that's the weight of the truck on the ramp, and that is being supported by the normal force of ramp pushing up on the truck. So basically the ramp is supporting that part of the weight. The part of the weight that's not being supported is this component here, and that's the force with which you're pulling up. Now, what they're saying here in your text is what is this force down here. Now, here's where we get into a little bit of geometry. Okay, we know this is supposed to be a right angle right here, right? And this is your angle theta. So that makes this angle up here the complement of theta. Okay? Now, because this is also supposed to be a right angle, that means this is also a right angle, and the stupid thing won't do it again. A right angle here, which means that is. So if this is the complement of that angle theta, then this is a right angle here, so this is also would have to be your angle theta, because it's the complement of the complement. Okay, so that would be your theta again. And what they said is to verify that this force here is F is equal to the weight times the sine. Goodness, this is not writing well at all. Sine of theta. Well, of course, the sine of theta, if this angle is indeed theta here, the sine of the angle is the opposite over the hypotenuse. The opposite is F over the hypotenuse, W, would be the sine of theta, and then multiply both sides by the weight, and you get F is equal to W times the sine of theta. Now, that's ugly, ugly writing, but the pen just was not wanting. But there we verified, and you did that in physics class, I'm pretty sure, too. All right, let's move on to the top of page 158. Now, let me see if there's anything I need to write here. An important problem in linear algebra involves writing one vector x as the sum of the scalar multiples of other vectors v1, v2, all the way up to v sub n. That is for scalars c1, c2, all the way up to c sub n. Here's what we're trying to do. I'll explain this a little bit more detail later. I'm using this because it's the only thing I'm going to write. Okay, here is some vector x. Now, of course, it has to be in the same dimension, same space as your other vectors are. They all have to be the same. And this vector we're trying to write as some linear combination c1 times vector v1 plus c2, some other coefficient, could be any coefficient, times vector v2 plus some other coefficient v3, c3 times vector v3 plus dot dot dot, goodness gracious, that doesn't do that well, all the way up to some c sub n times vector v sub n. Now I think they're using n here. Are they? Yeah. Okay. Now what we're saying there is you're given a set of vectors, the v's, v1 through vn, and some set of numbers, c1 through cn, and this vector x written as a linear combination of those other vectors. That's what we mean by that. And that's the reason I wrote this down, and that's what it's called. X is called a linear combination of those vectors v. So I guess I should write that down. Vector x is a linear combination I'm going to abbreviate of your v's. V1, V2, V3, dot, 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 all the way up to V sub n. It's a common linear combination of those other vectors Vn. That's something we'll be doing a lot. Of course, we aren't going to be doing a whole lot because we're going to run out of term. And in case y'all are concerned about it, I am too, but this was supposed to be a 10-week summer term. Okay, and if you'll notice, we have met 1, 2, 3, 4, 5, 6, 7 weeks. Today we'll finish 8 weeks. Thursday will be 8.5 weeks. Hey, this is not a 10-week summer term. This is an 8.5-week summer term, and that half Thursday is supposed to be final exam day. That's why we're going to do a little bit of linear algebra that day too, because I just going to try to cram in as much as possible. I think I said this at the beginning of the term, but I'll say it now. I'm apologizing to you for this, but here's the reason we had to do it this summer, this way. All the two-year schools, I think, in the state of Alabama are in just about the same boat. There may be a few that can do a 10-week term, but I kind of doubt it. Here's what's happening. We are changing, we the college, and James, you're probably the only one that's really going to be, are you finishing this term? James? James? Are you finishing this term? Is this your last term? Or are you coming back in the fall? What's that? I couldn't hear. James, what was your answer? Wait, say again? My internet is unstable. Okay, please say your answer again. Okay, what do you say, James? My internet went out on me, so I couldn't hear you. Okay, I just got a flash on my screen that's, oh, now everything's shutting down. This happened yesterday. Goodness gracious. Okay, I see you back again. Can you hear me? Okay. My internet just shut down and suddenly it was trying to reconnect. My internet down in the corner, I don't know if you can see this, it was all good. Blazer 1999, internet access, everything was perfectly fine, and yet it cut out on me. So sorry about that. But what I was saying, James, you're back. I never did hear your answer. Are you back in the fall or are you finishing this summer? Okay, in the fall. So none of you are going to be affected by this unless you come back next summer. Okay, but we are changing. The college, Lawson State, is changing everything. Our system, the Alabama Community College system, is making all the schools do this. We're changing from that old operating system that we've used ever since I've been part of Lawson, which was 2005. I was at Western State Technical College from something like 97, 96, something like that. Say again? Is it cut out again? I'm so sorry. Okay, I'm back. Okay, can y'all hear me? Okay, sorry. I I think it's a Zoom problem. My internet's great. The It said there was no internet, but every time I looked at it, the internet was good. It said it had internet access, but I think Zoom is just really, I think they're overwhelmed. I don't believe they are strong enough to support all the people using it. There's not a there's not a bit of wind, there's no rain, there's no storms, there's no reason that the internet would have gone out. I think it's a Zoom problem. So sorry about that. Okay, I can't even remember where I left off. I was just griping to you that they've shortened our term, but the reason is our college and all the other 2-year schools are having to go to this brand new operating system called Banner. We've been on an old thing called Alliant, which is ancient, and we should have been off of it years ago. But our down in Montgomery, they decided, that's the headquarters of the American Alabama Community College System. They've decided everybody has to be on the same system. So that is happening at the end of this month. So they had to get all the grades in the old system so they can shut down the old system and bring up the new system on the 31st. So therefore they said we had to have all this done by then. So why they chose the 23rd, I don't know, but they said the 23rd is the last day you can put. No, 23rd is next Thursday. The following Monday, well, that's getting awfully close to the end of the month. So anyway, that's why we have a short term. Sorry about that. Okay, I shouldn't have taken that much time to do it. Maybe the system shut me down because they didn't want me telling them that, but I told it anyway. Let's do example 6, okay? So let me get the screen share back to the there we go, to the whiteboard. And here we are. So now I have to move everything around. Y'all can't see this, but I can. This taskbar down at the bottom is smack in my way, so I have to move that down as far out of the way as possible. The taskbar at the top of the whiteboard is in my way, so I move it out of the way as far as possible. And of course, James is in the way. I've got to move him as far over as I can. Okay, and then I've got to scoop my whiteboard as far as I can in the opposite way so I get the most amount of writing space. There we have it. All right, so here we have the problem. This is example 6 on page 158 if you're following this. Here is a vector x. Okay, I started to turn off the Screencast-O-Matic while we had all that dead time, but then it kept coming back and I thought, okay, we're going to get back in. So there's a bunch of dead time there. Sorry about that. I forgot to turn it off early on, but yeah, I never did turn it off. So here's vector x. Okay, -1, -2, -2. Can someone tell me what space we're in? I'll be writing down the next one where you're deciding. Here's vector u. Vector u is 0, 1, 4. How many components do you see? 3. So we're in 3 space. Okay. Vector v. Yeah. Okay. -1, 1, 2. Yuck. And vector w. I don't know if I'm going to get it in here. I'm going to try. 3, 1, 2. Okay. And now they tell us the answer to what I was just saying. all these four vectors here are they're all in R3. You can tell that by the number of components. Okay. Now it says find the scalars A, B, and C. So we're looking for A, B, and C. That's what we're looking for, such that, and here's what we want to be true, X, vector X, is equal to A times vector U plus B times vector V plus C times vector W. Okay. Now, basically we do just about, hopefully, what you would think the logical thing to do. We write vector X what it is, and that's negative 1, negative 1, so that's a negative 2, negative 2. This drives me nuts. Okay, that's ugly, I admit, okay? And that's supposed to be equal to A times 0, 1, 4 plus B times negative 1, 1, 2 plus C times 3, 1, 2. Okay. Now, basically, you can write down an equation. I'm just going to flip things around on you a little bit and write it this way. 0 times A, I'm just going to leave that 0. Minus 1 minus B plus 3C is equal to minus 1. You see what I've done? A times 0 is 0. Minus 1 times B is minus B plus 3 times C. That has to equal minus 1. Second line, second number there would be A plus B plus C is equal to minus 2. In other words, 1 times A plus 1 times B plus 1 times C is equal to minus 2. And the third equation would be 4A. Can you pick up and go from there? Is equal to? Perfect. Guess what we got? We got something we can solve with matrix algebra. I would say, why not good old Gauss-Jordan elimination? Now I'm going to skip a step or two here and make it a little easier on myself because I get tired of writing this. I'm going to exchange these two rows, these two equations right there, and make the first one to be 1, 1, 1, negative 2. Second equation would be what? Third equation, third line, 4. I wish I'd been paying closer attention. Okay, I will now. Okay, what I'm going to do is divide everything in row 3 by 2. You okay with it? So I'm going to, boy, the first one will be a 2. second will be a 1. Okay, it's going to be a 1, 1 minus 1, right? Okay, so let me do them all at once. That'll be a lot less time. No, come on back here. Okay, 1, 1 minus 1. Okay, what you think the next thing I'm going to do? Okay, I will ultimately, that's a good idea. I think I want to get rid of this one first though. Negative 2 times row 1 add to row 3. Okay, and then let's go on and do what you just said. Row 1 plus row 2. Except, yeah, that will still work. You're doing it strangely, but it's okay. Actually, it's pretty good. I like it. Okay, so let's do, no, it won't. That's going to mess up that 0. You see that? You tried to talk me into something, didn't you, James? Huh? I'm not going to have it. Okay, this has got to go away at some point. Please go away. Okay. I'm not talking about you, James. You can stay. Okay. But you see, by adding those two together, we wind up with a 1 down here. We don't want a 1 down there, do we? Say no. Oh, wait. What were you adding or subtracting? Okay. Oh, and make the new row 1. Oh, got it. Yeah, we can do that. That'll be all right. Okay. Row 2 plus row 1. I thought you said it the other way around. I mean, it works both ways, but okay. So what you're doing 2 steps at once. Let's do this one first. Negative 2 times row 1 plus row 3. And that will give you a 0 here. Negative 1 there. Negative 1 there. Positive, yeah, 3, isn't it? 3 there. Okay. Now, we're going to add row 2 to row 1. The rest of you have to follow James' logic here. That's going to be a 1, a 0, a 4, and a minus 3, right? Okay. Now, if that's not enough, let's just change the signs of everything in row 2. In other words, multiply row 2 by minus 1. Is that okay? 0, 1, minus 3, 1. Okay. Boy, we did a lot of steps at once there, didn't we? Okay. Now with that one, we'll go on and take care of row 3 by adding row 2 and row 3. So let's do that one. If I can get my pen to come back, there it is. Row 2 plus row 3 is a new row 3. Okay? So that will now be, row 1 stays the same, 1, 0, 4, negative 3. I sure hope we haven't botched up something here, but we're going to try it. 0, 1, minus 3, 1, and this becomes what? And 4. These 4s are not writing well at all. That's a minus 4 and a plus 4. Okay, guess what we want to do next? So again, divide, divide the bottom row by minus 4, making a 0, 0, 1, minus 1. Okay. And the top row we'll leave alone for now, 0, 1, 0, 4, negative 3, and a, you know what we should have done before I did that? Let me back off a moment here. James, I'm surprised you didn't have me do it. Yeah, come on, pen, get there. Okay, there it is. Okay, okay. Here's what I would suggest before we did that. Let's add row 3 to row 1. Yeah, and that way you get a 0, 0, 0, 1. Okay. Now we'll write down row 2, 0, 1, minus 3, 1. All right, last step is 3 times row 3 plus row 2, right? Get rid of that one. Let's see what that gives us. We already know A is equal to 1 because 0, 1, 0, 0, 1. And then let's do what we just said here. Row 3 is 0, 0, 1, minus 1. C is equal to minus 1. And then doing what they said here would be a 0, 1, 0, minus 2. Did I do it right? 3 times row 3 plus row 2. 0, 1, 0, minus, yeah, okay. So, what we know is, it said find these three. Here's what they become. A is equal to 1. B is equal to negative 2. And C is equal to negative 1. Okay, let's see if that works. Well, that's going to be kind of hard to do. Let's try it. 0 times 1 is 0. Minus 1 times minus 2 would be 2. And minus 3 would be minus 1. So the minus 1 works. Then let's do the second one. And that would be 1 minus 2 would be a minus 1. Plus 1 would be, no, minus 1 would be minus 2. That works. Okay. Then do the third one, and that would be 4. Minus 4 is 0. Minus 2 is minus 2. Yep, that works. There are A, B, and C. Okay. Now all they say here is solve for A, B, and C, and you get A is equal to 1, B is equal to minus 2, C is equal to minus 1. Now, how they write, ooh, that was my fault. That wasn't anything the thing did. Let's see, I want to erase. Okay, now, may not need that anyway. Here's what the bottom line is here. This is now saying X is equal to U minus 2V minus C, minus W. That's same thing the book got. Okay? Now, they say something at the bottom of the page. Okay, a couple things. First, there's a discovery here in the column. It says, is the vector 1, 1 a linear combination of the vectors 1, 2 and negative 2, negative 4? Can anyone answer that question right off the top? No, you can't answer, or the answer is no. Why is the answer no? Okay. All right, but that's just one possible linear combination. It says, is there any possible linear combination? And your answer was right, no. but the reasoning wasn't quite adequate. Okay, and here's why. Look at that the first vector 1, 2, the second vector negative 2, negative 4. Notice the second vector is a multiple of the first one. Okay, therefore, basically they're effectively the same vectors. So you can't get another vector out of a linear combination of the same vectors. If you tried to do Gauss-Jordan elimination like we just did here, you'd wind up with a row of zeros and not be able to do it. It would not be doable. Okay? Now, it said similarly to determine whether the vector 1, 1 is a linear combination of the vectors 1, 2, and 2, 1. Okay? I'll tell you, 1, 2, and 2, 1 are not multiples of each other. There's no way you can get that. So they are linearly independent of each other. So there is a way to do it. Okay? But it's not intuitively obvious what that way is. If you were to subtract that first vector from the second vector, you would get a 1, negative 1. That won't work. You'd have to do it the same way we just did. A times 1, 2 plus B times 2, 1 is equal to 1, 1. So let's see if we can do that real quickly. Let me actually write it down. So let me get my pen in hand. Let me clear. Come on, where are you? Oh, my finger won't make it move. Okay, here we go. I'll clear the drawings. Okay. Okay. Now, basically what you would do is A times 1, 2 plus B times 2, 1 is equal to 1, 1. Okay? So that would be if you multiplied these out, you'd have A plus 2B is equal to 1, and 2A plus B is equal to 1. Okay? So that would be 1, 2, 1, 2, 1, 1 minus 2 times row 1 plus row 2 would be 1, 2, 1. This will give you a 0 minus 3 minus 1. It would be ugly, but it's doable. Okay? You're going to have thirds and all sorts of things in there. Okay? Basically, you can tell from the bottom here that minus 3b is equal to minus 1. So b is equal to 1/3. And because a plus 2/3 is equal to 3/3, then you would have a is equal to 1/3. Let's see if that works. Get the pen on that. 1/3 plus 2/3. A and B are both 1/3. 1/3 plus 2/3 is 1, and 2/3 plus 1/3 is 1. Yeah, that works. So there. Say again? Was there? Yes. Are you hearing me? Okay. Was there a question? All right. Okay, it seems to be happening today, doesn't it? Oh, okay, I know, but I mean, I don't know why it's so unstable, but it seems to be. Okay, now, number 3 says, what's the geometric significance of questions 1 and 2? Well, question 1 says, if the two vectors are linear combinations, if one vector is a multiple of the other vector, then you can't form a linear combination to get a third vector. The second one said if they're not, you can. Okay, so that's the geometric significance. The first two are multiples of each other, so they're basically extensions of the same vector. You can't get a new vector out of that one. The second one, those are not extensions of each other, so you can get any other vector out of those two. Number 4, is every vector in R2 a linear combination of the vectors 1, -2 and -2, 1? And the answer is yes, because those are linearly independent of each other. Now, how can you tell? Do your determinant, and you get 1 plus 4 is 5. It's not 0. So if the determinant was 0, then they are linearly are dependent on each other. If they're not, you got it. So anyway, that was the discovery. And then it says at the bottom of the page, page 158, you will often find it useful to represent a vector u, and this is in Rn, or I like to call it n space, or u1, u2, u3, all the way up to u sub n. In Rn, that's what they call it. Sorry. Either as a 1 by n row matrix, or row vector, or an n by 1 column matrix or column vector. Yeah, that's what we sometimes do. That approach is valid because the matrix operations of addition and scalar multiplication give the same results as the corresponding vector operations. That is, if you add u and v, that's adding column vector u plus, or column matrix u to column matrix v, you get u plus v. Exactly the same. Or if you had row vector u to row vector v, add those together, you get row vector u plus v. Okay? If you were just adding them together, you get the same answer, no matter which way you got there. Okay? Same thing applies to scalar multiplication, and the only difference is in each set is notations is how the components are displayed. They're all the same operations. Okay, that was sort of nebulous at the end, but it's there. Homework exercises 4.1. Do number 1. It should be at calcchat.com. Do either 3 or 5, or both if you choose. They should both be at calcchat. Either 7 or 9 or both. They are both at calcchat. Any of the odds 11 through 15, they are at calcchat. 17 should be at calcchat. Any of the odds 19 to 23, they should all be at calcchat, just like some that we did earlier. 25 and or 27 should both be at calcchat. 29 and or 31, they should both be at calcchat. 33 should be at calcchat. Either 35 or 37 or both should be at calcchat. 39 should be at calcchat. Any of the odds 41 to 45 should be at calcchat. 47 and or 49 should be at calcchat. 53 should be at calcchat. I'm sorry, 51 should be at calcchat. 53 should be at calcchat. Now they say there you might need some software program to help you with that one. I think you can probably do it without it, but you can see. Okay. 55 should be at calcchat, and then there's a true false 57 with 2 parts, so that should be at calcchat. There's a writing, if you want to look at that and see what they would have written, that should be at calcchat as well. I hope, I don't know for certain. 61 should be at Calc Chat. 63 is a proof. It should be at Calc Chat. 65 or 67, I think, are both proofs, or at least steps in proofs, and they should be at Calc Chat. So you can do any of those. Now, section 4.2 is named exactly the same thing as chapter 4 is named, vector spaces. The chapter name is vector spaces, the section name is vector spaces. There are two objectives here that are shown at the top of page 161. Let's go into a little bit of nomenclature here first. First, the definition of a vector space. Now, if you go back, well, I'm sorry, if you look down the page, theorem 4.2, no, I guess you do go back. I was thinking, I'm not finding 4.2. Oh, there it is, yeah. There's 4.1. 4.2 on page 156. I'll turn right past it. Theorem 4.2 on page 156 listed the 10 properties of vector addition and scalar multiplication in Rn. Okay, 5 of those were vector addition, 5 of them were scalar multiplication. Okay, suitable definitions of addition and scalar multiplication reveal that many other mathematical quantities, not just vectors, for instance, matrices. If you have the properly sized matrices, in other words, matrices that are the same sizes, all your matrix addition properties fit right with those first 5 properties of your scalar vector addition. You can do a scalar coefficient times a matrix, and if you do that, those second 5 properties all follow. Okay, so matrices follow those same vector space properties, okay, even though matrices are not vectors. But guess what? If you have polynomials, especially if those polynomials are of basically about the same degree, I don't want to say exactly, but about the same degree, then all those first five properties of adding vectors together, they also work for polynomials. The next one's scalar multiplication of vectors works for scalar multiplication of polynomials. Wow. Functions, as long as the functions are, similar enough, you don't want to do exponential functions added to trig functions or something like that. Technically they still work, but they're rather bizarre. But if you have functions, they share those same 10 properties. If you add them, they come out right. If you multiply just by scalars, not multiplying functions, multiplying scalars by the functions, those properties do. So any set that satisfies those properties, now we're going to call those properties axioms. Now it seems like to me that should be axia, because that's from a Greek word, and the plural of that should be but they're putting axioms, is called a vector space. So if whatever your collection is, whether they're matrices, functions, polynomials, whatever, or vectors, okay, if they obey those 10 properties, 5 of addition, 5 of scalar multiplication, then that can be classified as a vector space. And those objects are now classified as vectors. Even though it really is a matrix, you can call it a vector. Even though it really is just a polynomial, you can call it a vector because it obeys the rules for a vector space. Okay? It is important to realize that the definition of vector space below is precisely that. It's a definition. Okay? It's not a rule or anything else. You do not need to prove anything. You're simply listing the axioms or axia required of those vector spaces, because that's all it is. It's defining what a vector space is. That type of definition is called an abstraction. Why they're throwing all these terms at you, I'm not sure, because you're abstracting a collection of properties from a particular setting. Okay? R sub n was your original setting, vectors in real space Rn, to form axia for a more general setting. So, here are those same 10 properties again, and again, and again. Let V be a set on which these two operations, vector addition and scalar multiplication, are defined. Now notice they didn't tell you how to define it. Okay? They just said they are defined. Now, sometimes it's up to you to choose that definition. Other times it's already chosen for you. But we've got to have these two operations have to be defined. If the listed axioms that are listed here are satisfied for every u, v, and w in that space V. Now I think my phone's ringing. Let me see if it's anything important. I think not. Okay. Let me just tell you this. I think I mentioned it earlier. It looks like every hour, half-hour segment that I've got on the next 3 days, not quite, but close to them, for advising, they're all filling up like crazy. So that means less time to do grading, but I'll try to get it done. I will work very hard at getting it done. Okay, so anyway, let's get back to this. So we have these two operations, vector addition, scalar multiplication, defined some way or another. Any way you want to define them, do it. If then these axioms that you have are satisfied for every u, v, and w in that space V, okay, now that's a set of whatever. They don't say what it has to be. The set on which those two operations are defined, and if for every u, v, and w in that space, whatever they are, okay, polynomials, functions, vectors, matrices, whatever they are, if you have those and your two defined operations, addition and scalar multiplication, if these axioms are defined for every u, v, and w in that space, and every scalar number C and D, two numbers C and D, then V, that collection, that set, is going to be a vector space. So notice a couple things. Every vector space is a set of things that you're looking at. They could be polynomials, they could be functions, they could be matrices, they could be vectors, they could be any set of things you're looking at. You've defined some way to add them, you've defined some way to multiply them by a scalar, and if those definitions work for every one of these axioms, then it's a vector space. And we'll go through them again. If your two vectors, okay, u and v, two things you pull out of that space that you've just done, that set that you've just done, if any two of them that you pull together, add them together, you wind up with another entity just like that that's also in that space V. If that's always the case, that means that those vectors, those objects, are closed in under addition. Now remember, you had to define how you're adding these things together. Okay? Now, if also any two of these objects you pull down, u and v, add them together, you get the same result if you add v plus u. Whichever two you pull down, add them this way, add them that way. If they come out the same, then that's the second. Then those two, any two like that would be commutative in addition. Also, if you pull 3 down, add these two together, add the first one to it, or add the first two together and add the second one to it, and they always give you the same answer no matter which way you did that. Then it's closed, that you got associative property of that vector, whatever those objects are, the addition of those. Now, here's a biggie. Don't neglect this one. V has to have a zero vector defined, okay, such that for any u that is in that space V, in that set V, that you multiply, add it to the zero vector, some vector you defined as a zero vector, you've got to be able to get that original vector back, okay? So in other words, there has to be a zero vector, okay? The fifth one, the last one, and the added addition part, for every vector u that's in V, you have to be able to find another one minus u that is going to be, when you add those two together, you're going to get the zero vector. That's why you have to have one. Otherwise, you wouldn't be able to get one. Okay, so that's the 5 addition rules. The 5 scalar multiplication rules. Any number C, you multiply it by any vector you pulled out of that set up above, okay? I'm just saying up above. Then if you multiply a C by any vector you pull out of there, you must also produce a vector that's in that set that you just pulled it from, okay? Also, if you multiply C, any number C, times the sum of 2 vectors you pull out of that space, you must have the same answer if you do C times the first one plus C times the second one. That's a distributive property of scalar multiplication over whatever those vectors were, vector addition. Number 8, if you take 2 scalars, any 2 scalars in the world, add them together and multiply them by any vector, any element you pull out of that set, you should get the same answer as if you took the first of those times that element plus the second times the element. That's distributive property of vector scalar multiplication, well, scalar addition over scalar multiplication. Okay, sort of strange. And there's the only associative rule you have, okay, and that's this one. Any scalar C multiplied by any scalar D times any vector you pull out of that space, that set up there, okay, that must be the same result as you get if you multiply these two scalars first and then multiply them by that vector u. That's an associative property of 2 scalars, 1 vector. And then the last one is the number 1 multiplied by any element you pull out of that set up there must produce the same element, u. All right. Now, these first 2 examples here is basically reproducing what we did back in 4.1. The set of all ordered pairs of real numbers, that's what we call R2, with standard operations of addition and scalar multiplication, that is a vector space. Before we just called it a space, okay? In fact, I may have called it a vector space, but any 2 vectors you pull out of there, V is V1, V2, U is U1, V1, U1, U2. You can do all of those things to them. It's closed under addition, commutative under addition, associative under addition. There is a zero vector. 0, 0 is definitely a vector in that space. And there is always, for any ordered pair you bring down, negate both terms, and you got the minus v, minus u, and you add, minus v, add them to v, and you get the 0 vector. Okay. Scalar multiplication works. C times v, you multiply c times each of the components, you got cv. Okay, it's closed under scalar multiplication. If you pull any two elements there, any two ordered pairs, add them together, you get a sum of ordered pairs, so they're ordered pairs, and then multiply that by a scalar. That's the same as you multiply the scalar by the first, added the scalar times the second, and so on. All 10 of those fits exactly. Okay. Example 2 basically is saying every vector space Rn is a vector space. Okay, every set of ordered n tuples, you have to have n of them in every one, with the standard operations of addition and scalar multiplication, that will also be a vector space because all those 10 rules apply, every one of them. Now, the next 3 are very different, okay? But you're still going to find out they're vector spaces. It says, show that the set of all 2 by 3 matrices. Okay, now we go till 1:15, right? Okay, we got 20 minutes. All 2 by 3 matrices, set of all 2 by 3 matrices with the standard operations of matrix addition and scalar multiplication, let's show that that is indeed a matrix, a vector space. Okay, so here's what we've got. I'm probably not going to go into gory detail, but it'll be way gorier than I wish I were. Okay, so here is, let me clear this. Okay. Okay. Now, here is matrix A. Now they already told you it's a 2 by 3 matrix. So that means it's going to have 2 rows, 3 columns. So the elements here are A11, A12, and A13, and A21, A22, and A23. All right. You have matrix B, also a 2 by 3 matrix. So that's going to be B11, B12, B13, B21. I can't write. I'm getting hungry. Okay, sorry. I'm losing it. Let me get a swig of something here. Get a little blood sugar boost here. Also cough like crazy. Okay, I can't write with that end of the pen. There we go. B22 and B23. All right. Now I'm not going to write everything down, but let's just talk about it. What if we were to add A to B? What would that be doing? That would be adding to B11 and A12 to B12 and A13 to B13 and A21 to B21 and A22 to B22 and A23 to B23. Right? Oops. James, look at you. You let me write down a 1 there. That's a 2. Okay, why did you do that? Okay. Okay, thank you. All right. Well, what do we have? we have a 2 by 3 matrix. The first element is A11 plus B11. The second element is A12 plus B12. The third element is A13 plus B13. In the second row, you have 3 elements. And so the sum of those two matrices is also a 2 by 3 matrix. And that's in your set. Because remember, the set is all 2 by 3 matrices. So, number 1 is closed. Number 2, what if you added these two matrices together? We just did, and we got what we just came up with. What if we added them in reverse order? Then you'd have B11 plus A11, B12 plus A12, B13 plus A. Hey, guess what? Those are the same, because A11 plus B11 is the same as B11 plus A11. Addition of numbers is commutative. Addition of these two matrices is commutative. So number 2 is met. Okay. Number 3, associative. Okay. They only gave us 2. If you had a third matrix, okay, and you were to do the things to that, a matrix C, C11, C, yeah, and then you add those together, yeah, you get the same answer. When you added A and B first, you get A11 plus B11, then add C to it, you get plus C11. Okay? So you're going to get the same thing. You needed the third matrix there to do the third one. Okay? They only gave you 2. But you can just make up a third one as well. Okay? It's the only one like that. Now, does this space that we're talking about, the set of all 2 by 3 matrices, is there a 0 matrix in it? Zero, 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 0, 0, 0. Yeah, that's a 0 matrix. Okay? And when you would add, say, B to that matrix, you would get B. Add A to that matrix, you get A. So yeah, there is a 0 matrix, and any matrix from that set of other matrices that you add to that 0 matrix, you're going to come out with the same matrix you had to start with. So there is a 0 additive identity element. Now, the next one, is there some matrix in that space that when you added it to A, you're going to get the 0 matrix? Sure. Negative A11, negative A12, negative A13, negative A21, negative A22, negative A323. That will give you, when you add it to A, you're going to get the 0 matrix. Okay? So there is a minus A. A plus the negative of A is going to give you the 0 matrix. So all 5 of the first 5 are done. You had to add in a C matrix. They didn't say you had it, but just throw one in. Okay? Now, let's look at the scalar multiples. If you multiply the A there by a scalar C, then what you do is multiply it by every element in that. You get CA11, CA12, CA13, CA21, CA22, CA23. Guess what? That's a matrix in 2 by 3 space. It's a 2 by 3 matrix in that space that you were started. So it's closed under scalar multiplication. That's number 6. Now, here's 7. Let's see if we can get this one written out here. Let me first see if I can get my y. Oh, why is this? Oh, there it is. Okay. Let me see if I can get that erased. Okay. Now, C was, number 7 was, if you take some number C times A plus B, okay, well, let's first add A and B together. We already have done that. A11 plus B11 plus A22, yeah, you got them all added together. If you multiply C times that, you multiply C times A11 plus C times B11, okay? You multiply it by both terms, and that's the same as C times A plus C times B, okay? Because if you add these first and then multiply by C, then you can break that down as the C times A times C times plus C times B. Okay, I don't want to go into gory detail on that, but it's there. Perfect. Number 8, if you had two numbers, C plus D, and you multiply those by either one of those, let's just say matrix A, that would be C plus D A11 plus C plus D A12 plus C, no, I'm sorry, C plus D A13, second row, C plus D times A21, C plus D times A22, C plus D times A23. Well, guess what? Every one of those is a distributing two numbers over another number. The sum times the product. You can split them up and call that CA11 plus DA11, CA12 plus DA13, CA21 plus DA21. Just do them like that, split them up, and you get the same thing as CA plus DA. And that's number, what, 7? 8. That's number 8. Okay? Now, next one is probably just as easy or easier. If you had C times D times matrix A, is that the same as C times D times A? Well, let's see. C and D are both real numbers, any two real numbers. CDA1 plus CDA2, not plus. First element CDA1, second element CDA2, next element CDA3, CDA13, I'm sorry. Next element, second row, CDA21, CDA22, CDA23. Okay. Now, every one of those had a C in it. Factor that out, and what you have, C times D1, D2, D3, the A11, DA12, DA33, second row, DA21, DA22, DA33. Well, that's exactly C times DA, of course. Okay, so that works. And the last one, if you multiply the number 1 by either one of those matrices, you're going to get the same matrix. A11, A12, A13, A21, A22, A23, or the other one. So yes, all 10 of those rules work for 2 by 3 matrices. Okay. Now, they say on the side there that in the same way that you're able to show that all 2 by 3 matrices work, you can do the same thing for the set of all M by N matrices. It doesn't matter how many elements you have there, as long as all the matrices are exactly the same size, M by N. Then you can add them, you can multiply, you can do all the things, and they all work. So then what we say then is we denote that by, here's the shorthand for it. For this one, that would have been M23. That would be a vector space. What we're just talking about is M, M, N. Yuck! Did it again. Okay, that's a vector space. That's how we abbreviate it. M standing for the matrix, capital M for the matrix, little m for the number of rows, and little n for the number of columns. Now, I'm going to clear the screen here. Okay, we got 7 minutes. Will we be able to do example 4 in 7 minutes? Let's see. Now, remember when I got to the polynomial part, I kind of weasel worded my way around that. I said, as long as the polynomials are sort of similar enough, okay? And here's what they mean. I mean by that. Here's a definition, capital P sub 2. What does that mean? That is the set of polynomials. That's what the capital P stands for. Polynomials, I'm going to abbreviate it like crazy, of the form little p of x, this is a polynomial, is equal to, now this is written sort of in reverse order of how we usually write it, but just to get the subscript numbering right, a sub 0 plus a sub 1 x plus a sub 2 x squared. Polynomials, all the exponents have to be whole numbers, and they have to be added or subtracted. They have to be added or subtracted. The a's can be any kind of real number in the world, but the exponents can only be whole numbers. So that would be a set of all polynomials of this form. Now, how we shorthand that is say all polynomials of degree 2 or less. Okay, because if your a2 here was a 0, that would be a linear, but it's still of degree 2 or less. Okay, you couldn't have an a cubed in it, x cubed in it. It couldn't happen because this is p2. All polynomials of degree 2 or less. Okay, and your a1, a2, and a3 are, a0, a1, and a2 are all real numbers. Now, what if you were to add two polynomials like this? Let's call it p of x and q of x. And it also is in p2, meaning it's a degree 2 or less. That would be b0 plus b1 x plus b2 x squared. If you were to add those two together, and every time that comes on, it wipes out something. Okay, there, last thing I wrote. All right. If you were to add those two together, guess what? You still get a polynomial of degree 2 or less. Okay. You can't add those two together and somehow get an x cubed. It just won't happen. It will not happen. You will get a degree of polynomial. So that would be closed under matrix polynomial addition. Okay, you have to define what your addition. You add term by term. Okay, and scalar multiplication, you multiply every term by the same scalar. Okay, standard way of doing it. Okay, so what if you added p plus q, but then added q plus p? Same thing. All you're adding are your coefficients, and the coefficients are numbers, and real numbers commute. So your polynomials commute. Okay? Associate, you'd have to have a third one, p, q, r. Let's call the next one r of x. If I could get the pen up here to do it. R of x. It has to be in p2, so that would be, say, c0 plus c1 x plus c2 x squared. So if you added the first two together and then added the third one to it, you'll get the same thing as if you added the first to the sum of these two. Again, you're just adding the coefficients, the real numbers. Real numbers are associative under addition, so are your polynomials of degree 2 or less. Adding any of those together, you won't ever come up with a polynomial of degree 3 or anything higher. You won't come up with anything with a negative degree. Can't do it. Won't be a polynomial. Okay? Now, by the way, the book goes into what the I said what the addition and multiplication would be, scalar rules would be, and the book goes into that. Okay, so we've done addition, we have closure, we have commutative addition and associative addition. Okay, what's the next addition one? A zero vector. Does this have a zero polynomial? Yeah, 0. Okay, that's it. 0, C, or whatever your first thing. A0 would be 0, A1 would be 0, A2 would be 0. Yeah, that's the 0. Add that to any other polynomial of degree 2 or less, you're going to get the same polynomial you had before. Add that the 0 polynomial to B, you get, or Q, you get Q. Add the 0 polynomial to R, you get R. Add the 0 polynomial to P, you get P. Okay? Now, that's the fourth one. The fifth one are, is there an additive inverse? Sure there is. Just negate everything. Minus A1, minus A1x, minus A0, minus A1x, minus A2x squared. Add that to A0 plus A1x plus A2x squared. And guess what you get? The 0 polynomial. You get 0. Nothing. They all disappear. You get the 0 polynomial of degree 2 or less. Okay. Now, that's the only thing that's a little bizarre here. We're not used to writing 0 plus 0x plus 0x squared. We're usually just writing it 0. But that's a polynomial of degree 2 or less. So that's perfectly okay to write it that way. Okay. Now let's get to the scalar multiplication. If you multiply any one of those polynomials by some letter D, let's say, then you'd have dA0 plus dA1x plus dA2x squared. Well, that's a second degree polynomial. So it's in the set of polynomials. So it's closed under scalar multiplication. And the next one is, if you multiply the same scalar by the sum of two of these, this gets really old fast, doesn't it? That'd be C times A0 plus B0 plus C times A1 plus B1 times X plus C times A2 plus B2 times X squared. Put them in parentheses. Yep, you get C times P plus C times Q. You come out the same answer. Okay. Next one, if you were to add two scalars, C plus D, multiply that by A, that'd be C plus D times A0 plus C plus D times A1 x1, x to the first, plus C plus D times A2x squared. Well, since they all have the A0, A1, then split them up, and that'd be C times P plus D times P. Yep, it gives you exactly number 8. Now, wait, that was 9. I think I'd already done 8. Okay, and then of course, if you multiply any one of those polynomials by the number 1, you get the same polynomial. That's the multiplicative identity element. So, sure enough, set of all polynomials of degree, and I'm going to expand this, degree n or less, they are vector spaces. Can you say the set of all polynomials is a vector space? I don't know. You really need to define degree n or less. Okay, 7 or less, 4 million or less. It's really a good idea to define that. Okay, that was example 4. How are we oh, we've just run 2 minutes over, and I'm not going to charge you any extra for that. So we'll pick up with example 5 next time. Let me give you a few homework exercises to work on. and that would be, I think you can do either any of the odds 1 through 5. This is on page 166. I think you can do any of the odds 7 through 11. I think you can do, wow. I think you can do any of the odds 13 through, wow, 35. Okay, maybe not. Some of those, they define some sort of strange addition or multiplication principles. So if any of them stump you, hold on. We'll probably hit the rest of those. Stop there though, and try to do as many of those as you can. All right. Any questions, issues, concerns? Okay, if not, I'm going to stop the sharing. I'm tired of sharing now. Okay? And we'll also end the recording, unless there's some question. Anyone got a question? All right, I'll end the meeting for all of us. We'll see you on Thursday. Please, folks, try to get me some of your papers and tests in. And if I were you, I wouldn't worry about doing any more problems. Just get me the work that's already been assigned. That will be your input for this week. Okay? There's plenty of it out there. Just get me your work. Okay? Now, if you want to do problems, just to make sure, please do them. And if you want to turn in the end because you're not sure if you're doing them right, please do that as well. But don't just turn them in just to say, oh, I need something from this set. Only if you have questions about it. Okay? Good deal. We'll see you on Thursday.